On the safety day, the wind speed was 0.5 meters per second, so that the two wind turbines cleared the chamber of vapor in about 2 minutes. This result was a surprise to us, as we had estimated it would have taken 5 minutes to disperse the vapor. In our experience, ventilation also increases the lifetime of the devices inside the chambers by removing moisture. We recommend ventilation for all spaces with a volume of more than 50 litres. If the chambers are not ventilated, filling them with non-combustible material will increase safety. If there is a risk of vandalism or terrorism, we recommend filling the chambers under all conditions, even if they have ventilation, as is required in Sweden. When building a filling station, it is also very important to remember that vapor can spread around the forecourt and the garage via sewerage pipes and electrical wire protection pipes. Vapor barrages are extremely important to prevent vapor or a possible explosion from moving underground. Explosions are always possible when handling petroleum fuels. The idea that nothing happened last time can be very dangerous. Two things are needed to create an explosion: a detonator, which can be a match, a cigarette, or a spark, for example, and an explosive, in this case a mixture of petrol vapor and air. The right explosive mixture of air and vapor depends on the wind, the temperature, the type of fuel, airflows from surrounding objects such as trucks, and of course the space in which the explosion takes place. We tested the power of an explosion with a cup of petrol and a 300-litre open well, using a conventional fuse as the detonator. Our plan was to observe the way an explosion can move along a pipeline. For most of the people present, the power of the explosion was an incredible surprise. Remember that this was only a cupful of petrol in a 300-litre well. As we have demonstrated earlier, dealing with petrol vapor is a part of the everyday work at a filling station with a vapor recovery system, where enough vapor is generated to fill 1,000 to 2,000 litres of open space, so that the explosion would have been 3 to 6 times more powerful. In this test, the explosion did not run along the pipeline, as the pipe was torn apart by its power. If the well and the pipeline had been underground, the situation would have been totally different. We also tested the explosion in a well filled with aluminium sacks containing lacquer aggregate. As we can see, filling the well does not prevent the explosion, but it does greatly reduce its power and the danger attached to it. To demonstrate a real overfilling situation with real equipment would of course risks to the onlookers, and we therefore decided to test the chain reaction that would occur if one of the tank connections were left open during unloading. A filling pipe or level measuring pipe, for instance, or if there were a broken gasket. The vapor released is directly related to the volume of fuel being unloaded. In normal cases, we are talking of several thousand litres, as the vapor released exceeds the lower explosion limit many times over. A volume of 100,000 litres of explosive vapor could be released into the air in the case of an accident or human error. Unloading was simulated by using compressed air at 0.03 bar. In this case, the vapor spread over a danger zone of 5 to 7 meters around the open pipe connection when the access chamber cover was open. If we were to estimate the results in a real unloading situation with a gentle wind, The danger area would be at least double this size. Overfilling also creates other risks if the fuels have access to a sewerage system. The final test of the day was a car fire on a forecourt. The idea was to examine the effects of the fire on materials and structures. This is a very rare incident, but when it happens, it can cause a number of other risks. We measured temperatures in the underground structures when a car was burning above the access chamber. Even when a burning tire of a car was directly above the access chamber, the temperature did not rise above 30 degrees Celsius. The conclusion is thus that the greatest risk of explosion comes from sparks if they have access to the chambers. The dispenser can also be a danger in this kind of accident, and if the car had burned for longer, it would have exerted a damaging stress on the canopy structure. For this reason, the trainee fire marshals had to cool the canopy down during the fire. We have gathered some examples of risk management in a forecourt area. The ways of preventing one risk may have the effect of increasing another. We can all think of ways to improve safety at filling stations, but we must remember that there is always the question of cost. If we would think of a state-of-the-art filling station with all available technical solutions and round-the-clock surveillance, the building and operating of such a station would be so expensive that it would be hard to find customers to pay for it. Protected two-walled structures in tanks and pipelines. Properly working overfill preventers. Protective membranes in danger areas. Tight access chambers and tank sumps. Reducing pipelines to a minimum. And careful motorists and tanker drivers. A typical association with soil and environmental damage is that this has often happened over a long time and that it is very difficult to observe. The financial costs are also considerable. There are ways of preventing fuel thefts from filling stations, particularly underground storage tanks, offset filling points, filled access chambers, automatic fuel level gauges, or at least vapor-tight mechanical gauges, video surveillance, good illumination, and anti-theft alarms. The most important thing in preventing fires and explosions is that people should be careful. Other precautions include ventilation of open spaces, avoiding opening pressurized valves and connections, properly working overfill preventers, vapor barrages to block vapor from spreading to surrounding buildings and structures, tight non-sparking access chamber covers, non-burning ventilated filling boxes, a working and properly used vapor recovery system, and surveillance during public celebrations such as New Year firework displays. This video is not meant to scare people, but to guide ideas in the right direction when a station is being designed, installed, and operated. Serious accidents are extremely rare at filling stations. We all have the responsibility to create a safer, cleaner environment, and the journey to that target takes place in small steps, learning something new every day, and with continuous improvement.